Today's lesson is about tangent lines and how to determine if a line is tangent to a circle. Now, a tangent is different from SOHCAHTOA. It's not the trig function tangent, it's just a segment. And so before we start, let's go ahead and have a circle. So let's see. I'm just going to sketch a little circle down here. I'm terrible at drawing circles, so I'm just going to trace one. Okay. So before we get started, let's just really focus on vocabulary. So a tangent line is a line that touches the circle at one point. It also never goes inside of a circle. So a tangent line kind of goes to a circle, but never actually inside of a circle. So in this picture, this line would be referred to as your tangent line. And that line is called a tangent. The point where it touches the circle is referred to as a point of tangency. Okay, so that little blue point right here where the tangent line touches the circle is referred to as a point of tangency. The very important property about tangent lines is that when a tangent line touches a radius or a diameter, it makes 90 degrees. It will always be perpendicular to the circle if it touches at a radius or a diameter. Because remember, a diameter is just an extended radius. It's a double radius. So diameter, radius, basically the same concept in this kind of problem. So let's look at our first example. And actually, I'm going to do these a little bit out of order. I'm going to do the second example first because it's a little bit easier than the first one. So we'll start here first. So the question says, determine if line AB is tangent to the circle. So what I'm going to do is identify that tangent line. And in this problem, it's AB. If the line is tangent, angle A, where it touches the circle, will be 90. But we don't know if it really is 90. So I'm going to put a little question mark there because we're not 100% sure. The only way to prove it's 90 is to use the theorem that only works on a right triangle, which is called Pythagorean theorem. Sorry, I really can't spell and write at the same time and talk. Wait, I can't talk and write at the same time and actually spell the word correctly. So Pythagorean theorem is a squared plus b squared equals c squared, where a and b are the legs and c is the hypotenuse. Now this is different from law of sines, law of cosines labeling. A, b, and c just mean legs and hypotenuse. So let's go ahead and label. Across the 90 is always the hypotenuse, which we're going to label as C. In this case, it doesn't matter which one A or B is. So I'm just going to label this one as A and this one as B. From here, let's substitute. So 6.6 squared plus 11 squared has to equal 13 squared. If they don't equal, it's not a right triangle. And you can go back and watch the video on Pythagorean theorem and proving something's a right triangle. We did that basically in chapter 1 or 2. It was a long time ago, but we did talk about proving if something's a right triangle. Let's see. So what we're going to do now is just test it. I'm going to type in my calculator 6.6 squared plus 11 squared. Not to the negative. Having an off day. All right. So we get 164.56. Now I'm going to square 13. And when I square 13, I get 169. Now I'm going to just stop and compare. Did we get the same thing on both sides? Hopefully we can realize that 164.56 and 169, those are not equal. Therefore, remember that symbol means therefore, segment AB is not tangent to the circle. It's got to be the same on both sides. And when I look here, I get 164.56 and 169. Those are not the same number. For it to be a tangent line and for the Pythagorean theorem to work, it must actually be 90 degrees. Okay, let's try the next one. This next one is very tricky because it's trying to confuse you. So the first thing I'm going to do is label AB because it says AB is my tangent one, or it could be, we don't know. And then if that line is supposedly our tangent, angle A is our angle in question. Do we really know it's 90? We're going to prove it. Let's go ahead and start labeling. My hypotenuse is across the 90. But the trick here is to know that the hypotenuse is broken up into 8 units here and 12 units here. So we're going to use segment addition. 8 plus 12 is 20. Now, here comes the trick. How do we know the measurement of this segment? We got to pause, look at our picture, and kind of cover up some stuff outside the circle. So what I'm going to do is I'm going to cover up everything that's not in the circle. And notice how what's remaining is this 12. 12 is the radius of the circle. As a radius spins around a circle, it stays the same. So if we were to rotate 12 down here, this measurement would also be 12 because it's a radius. Now I have my full triangle, and if you can't really see it, take a second and just draw it out. It's not a big deal. This is 20, that's 12, and that's 16. So now, again, we're going to use Pythagorean theorem. We've got our side across the 90 as hypotenuse, making that our C value. So 16 squared plus 12 squared equals 20 squared. We're going to test that out. 16 squared plus 12 squared is 400. And then I'm going to go ahead and do 20 squared in here. And we notice we get the same number, 400 and 400. So 400 equals 400. That is a true statement. Therefore, AB is tangent to the circle. Notice the difference in these two answers. On this one, we get the same number on both sides, and in this one we didn't. Same number means tangent. Different number means not tangent. All right, let's hop on down to the next section. Find the segment length indicated. Assume the lines which appear tangent are tangent. So this is where we get to use our own personal judgment call. So looking at the first problem, the line that looks tangent to me is this 4 because it's not going inside of the circle. So that means it's safe to assume that this is 90 because it said in the problem, assume lines that appear tangent are tangent. So that lets me know I can put the 90 degrees with confidence. Now I'm going to label, and again, this is just the Pythagorean theorem. Across the 90 is hypotenuse, and that's my C value. I've got A and B, and that question mark is really just X. It's just a variable. So let's do Pythagorean theorem. Remember, it's A squared plus B squared equals C squared. A is 4. 4 squared plus X squared equals 8.5 squared. 4 squared is 16 plus X squared. And then 8.5 squared is 72.25. I'm going to subtract 16 from both sides. I get X squared equals 56.25. Square rooting. When I square root 56.25, I get 7.5, which is a decent enough decimal that we'll go ahead and keep it. Okay, let's try another. Okay, we're going to assume the lines that appear tangent are tangent, so that would be this question mark, because that's the piece that doesn't go inside the circle. I'm going to put my 90-degree box here. That means I'm going to go ahead and label hypotenuse. Sorry, I had to take a drink. Across the 90 is this full segment, which when I use segment addition, I get 2.5. Now again, I have question mark here, which is really just X, so we should be able to find this leg length without doing any form of math. So what I'm going to do is I'm going to cover up the outer portion of the circle. So if I cover this up, I should just see a radius and a radius. If the radius starts out at 1.5 as it spins around the circle, it's going to stay the same measurement. So that means that this length is also 1.5. Now that we have our pieces, we're going to go ahead and do Pythagorean theorem. Across the 90, again, was hypotenuse. We're going to label that as C, making A and B here. So x squared plus 1.5 squared equals 2.5 squared. So x squared plus 2.25 equals 6.25. When I subtract my 2.25 from both sides, I get x squared equaling 4. Square rooting both sides gives me an answer of 2. All right, let's try another one. Now on these bottom pieces, this is all about finding a perimeter. Let's see if I can. There we go. We want to find the perimeter of the polygon. Now there's a very special property involving tangent lines, and it says that if two tangent lines meet outside of a circle at a common point, those two lines are congruent. So the way that you do this is you go from the point of tangency to the common endpoint. Point of tangency to the common endpoint. That means that these two measurements are equal. And you kind of follow that all the way around the circle. So point of tangency to congruent point, and then back here it kind of looks like little beaks. And then let's see, we'll go from 11.2, we'll go here and here. The next thing you want to do is fill in all the missing pieces that require you to do literally no math. Okay, well if this little piece is orange and this one's over here orange, 10.5, 10.5. 11.2, 11.2. And then this 23.2 is the whole segment. So back in chapter 1 when we learned segment addition, add the two smaller pieces to get the bigger piece. So to find that missing piece, I'm going to do 23.2 minus 11.2. And the reason we're going to do that is because together I get 12. 12 plus 11.2 is 23.2. Once you break up the big segment, cross out that piece so you don't reuse it when you're doing perimeter. That's 12, this is 12. Next, I'm going to go ahead and add them all up. So 10.5, basically adding this, plus this, plus this, plus this, plus this, plus this. I should be adding the numbers twice. And I get a perimeter of 67.4. We're just adding. Okay, let's go through this last one real quick. I'm running out of some time here. So again, I'm going to match my numbers, 13, 13. So I'm going to go ahead and just put a 13 here. Okay. These two go here and here. Here and here, and that's going to be 4.6. And then I've got my last piece here. So what I'm going to do, 25 minus 13 gives me 12, and I'm going to divide that. 12 and 12. Then I'm going to do 21.8 minus 12 to give me 9.8. Cross that one out, and that's 9.8. So now to find perimeter, 13 plus 13 plus 12 plus 12, 9.8, 9.8, 4.6, 4.6. So 13 plus 12 plus 9.8, 4.6, we get a perimeter of 78.8.